All right. In this lesson, we are going to go over Rolle's theorem and mean value theorem. Both theorems are expected to be understood in AB and BC calculus, and in some college calculus courses and some other high school calculus courses, but not all. So let's jump into it. So we'll start with Rolle's theorem, which is basically a special case of the MVT, or the mean value theorem. I'll talk about that later. Sketch the graph of a differentiable function, so it's got to be smooth and continuous, such that -3, 2 and 1, 2 are points on the graph. All right, so -3, 2, I just picked arbitrary points for this, and 1, 2 are right here. Now, if it's going to be a function that is differentiable, we can't have any points, like any kind of cuspy points or corners, and it's got to be continuous. So I'll just kind of go like this, down, and like that. How about that? Just a random differentiable curve. Now, we're differentiable between -3, 2 and 1, 2. The question that I'm asking you is there at least one point on the graph between these 2 points such that we have a horizontal tangent line? Well, let's take a look. Not yet. Nope. Ooh, right about here, somewhere about there, we've got a horizontal tangent line. And I dare you, try to draw something that's smooth without somehow having a horizontal tangent line. You can't do it. And that's basically Rolle's theorem. It says that if you've got 2 points, 2 endpoints, and the curve between those 2 endpoints is differentiable, and we're continuous through that entire span as well, you're going to have at least one point where the derivative is 0, where you have a horizontal tangent line. And so I formalized that a little bit here on the next page. Informally, if a function has a smooth graph and 2 points with the same y value, right? That's what we had here, 2 points with the same y value. Then we know that the function must have at least one horizontal tangent line, or flat spot, between those 2 endpoints. So let me show you what I mean, and we'll pick 2 other random endpoints. So let's do -6, -2, and 2, -2. And no matter what you draw, as long as it's smooth, right, we can go up and down and up and down. No matter what, we're going to end up having at least one horizontal tangent. In this case, we had 1, 2, 3. We could have many of them. Think of it as what goes up must come down, right? If you're a differentiable curve, or if it's a horizontal line, still differentiable and still have a slope of 0. You might see this formal definition. Let me just read it to you, just so you're in good shape with it. If f of x is continuous, that's this, on the closed interval a to b, so this would be a and that would be b, and differentiable on the open interval, so from here to here we're smooth, and we have that the y value of each endpoint is equal. Then there exists a value c, so some x value between a and b, such that x equals c is on that interval, and the derivative is 0. That's really fancy pants notation for saying if we've got 2 y values that are equal, then we know as long as the curve's differentiable, we're going to have horizontal tangent lines. That's it. So again, what goes up must come down when it's smooth. Now what defeats this is if you have something that is not differentiable. So you've got 2 endpoints here that have the same y value, but we're not differentiable the entire time. And notice we don't have a horizontal tangent line. So you've got to be differentiable. Okay. So a type of problem that you might see in your textbook, or an example that you might see, is one like this. Find all values of x equals c. So find all the x values on the interval -4 to 4, so that's here to there, such that f prime of an x value equals 0. So essentially you're finding the critical numbers, given that f of x is this graph right here. And it says below, but it goes off to the side. So basically, first we got to see, does Rolle's theorem work? Well, this is a polynomial, and polynomials are differentiable everywhere. They're always smooth, they're always continuous. But notice from the graph that it is smooth and continuous on the interval. So Rolle's theorem will apply because we've got 2 y values that are the same. So we know we're going to have at least one place where the derivative is 0. From the graph, we see there's 1, 2, 3 places. So we'll do this one out mathematically. Pretend the graph's not there for a second. We're going to take the derivative, because we're asked what are the x values where the derivative is 0. So that's going to be 4x cubed minus 32x. Of course you pull out your GCF. Why wouldn't you? So 4x times x squared, and then that's going to be minus, what's that going to be? Well, if you're pulling out the 4x, that's going to be minus 8, like so. All right, no problem. So we're going to have 2 places from this where the derivative's 0 and 1 place here. So we said each part equal to 0. X will equal to 0 from this. X squared minus 8 equals to 0 when x squared is equal to 8. Don't forget your plus or minus. X is equal to -√8 positive root 8. And you could write that as 2 root 2 if you wanted to. We'll leave it here. And sure enough, here's negative root 8, here's positive root 8, and here's x equals 0, all places where we have horizontal tangent lines, which was guaranteed by Rolle's theorem. That's it. Very cool. All right, one last little note before we get into the mean value theorem in the next set of videos. I'm saying keep in mind that our function must be differentiable for this to apply. So here's one where let's say that you've got endpoints at, I don't know, x equals 1 or negative 1 and x equals 1, or you could do x equals negative 5 and x equals positive 5. However you look at it, we've got that the y values are the same as your endpoints. And while the curve is differentiable almost everywhere, it's not differentiable at 0. And it just so happens that because of that, we don't have a place where f prime of anything on either of these intervals, negative 5 to 5 or negative 1 to 1, we don't have a place where the derivative is 0. So just because the initial y values are equal, because the curve's not differentiable in that interval, we see that now, well, we don't have where derivative is equal to 0. So Rolle's theorem only applies again if the curve's differentiable on the interval. All right, that's it. Wanted to show you that one more time. I can't wait to see you in the flip side, video 2, MVT.